In this video, I'm going to go over inverse matrices as well as the identity matrix. What's the link between the two and how can you even use these in questions? So let's suppose I have a matrix. The matrix I'm going to give a letter capital A, and each of the elements inside this matrix are just the lowercase letters A, B, C, D. If I want to work out the inverse of this 2 by 2 matrix, okay, the inverse, the way I would work it out is by doing 1 over AD take BC, and then the matrix will simply become D, negative B, negative C, A. Okay, so this here is just the scalar multiple of 1 over AD take BC, and the matrix here, all you have to do is swap around the values of A and D and then simply negate the values of B and C. So in this equation here, the bottom part of this, the denominator of this fraction, is actually called the determinant of A. Okay, this here is called the determinant of matrix A, and you can also see it being written as the det of A. Okay, it just means the determinant. Okay, cool. I just taught you how to work out the matrix of a 2 by 2 matrix. Who cares? Why do I actually care about this? What benefit does this serve me? Here's what's cool about the inverse. If I have the matrix A and I post multiply it by the inverse, that is the same as taking the matrix A and pre-multiplying it by the inverse. And what this is just equal to, if you do either the matrix A post-multiplied or pre-multiplied by the inverse, it is simply the same as the identity matrix. The identity matrix is simply a square matrix which has 1 in its leading diagonal. So leading diagonal like this. Okay, it doesn't have to be a 2 by 2 matrix. It could also be a 3 by 3 like this. Okay, or even bigger, it could also be a 4 by 4 like this. Okay, but we in this video will only be dealing with 2 by 2 matrices. So this here is a 2 by 2, this is a 3 by 3, this is a 4 by 4, and any matrix which has the same number of rows as columns is called a square matrix. Okay, but again, for this video, we're just going to be dealing with the inverses and identities of a 2 by 2 matrix. Okay, so the identity matrix is the matrix equivalent of saying the number 1. Okay, this is saying the number 1. Okay, another way you can write the number 0 in a matrix form is saying the 0 matrix. The 0 matrix is simply a square matrix where all of its entries are just 0. Okay, so let us now do some problems with the inverse and the identity matrix. Okay, here we have 4 matrices, and our goal here is to work out the inverse of all of these matrices. So let's give this a shot. So first we'll start off with the matrix 3, negative 1, 4, negative 1. To work out the inverse of this matrix, we simply do 1 over AD take BC, and in this case A, D, B, and C are the following. This is A, B, C, and D. So AD take BC is simply the leading diagonals multiplied by each other, which is negative 3, minus these two times each other, which is minus 4. Okay, so that gives us 1 over negative 3 plus 4, which is just 1 over 1. Okay, and then we can do the matrix, times this by the matrix of negative 1, 1, negative 4, 3. All we did was swapped the positions of A and D, and then we swapped the signs from negative to positive and positive to negative of B and C. Okay, and another thing I needed to mention, in order for a matrix to have an inverse, okay, so let's say we have matrix A, okay, so if we have A, okay, the determinant of A must not be equal to 0 for it to have an inverse. Okay, so if you want A to have an inverse, the determinant of A cannot be equal to 0. And the reason for that is because if we have a look at our previous formula, we have 1 over AD take BC. If this determinant was equal to 0, wouldn't that just be 1 divided by 0, which is a big math no-no? Exactly, so we're not allowed to do this, hence we have to have the determinant not equal to 0. Okay, and if a matrix Okay, let's say the determinant of A was equal to 0. Okay, then you would say that matrix A is a singular matrix. You would say it is a singular matrix. So that's the last bit of theory. Let's go back into the questions now. So now let's work out the inverse of this matrix here. To work out the inverse, we do 1 divided by the determinant. The determinant in this case is 4 times 2. Take away minus 1 times 2. Times by, we swap the positions of A and D, and then we change the signs of B and C. So now let's work this out. 1 divided by 4 times 2 is just 8. Minus 1 times 2 is just minus 2. So this is 8 plus 2, which is just 1 over 10. Times by 2, 1, negative 2, 4. You can leave it like this, but if you want to, you can just expand the 1 on 10 to each of these elements. I'm not going to now, so we'll just move on. Now we have 3, 1, negative 2, 4. To work out the inverse of these matrices, all I'm going to do is the exact same steps as I did before. What we're going to do is 1 over the determinant. So in this case, 1 over 3 times 1 minus 2 times 4. 80 take BC is 3 times 4 minus 1 times minus 2. And then the matrix inside will be 4, negative 1, 2, 3. Swap the positions of A and D, and then change the sign of B and C. Okay, so now what we have is 1 over 3 times 4, which is 12, minus away 1 times minus 2, which is minus 2. So minusing away these together, we get 12 plus 4, 12 plus 2, which is 14. And then we have the matrix 4, negative 1, 2, 3. And the last one here, work out the matrix or the inverse of this matrix here. And we're going to say that K is a non-zero real number. So we first do the 1 over the determinant step. So the determinant in this case is AD, so 1 times K. Take BC, which is 0 times 0. And then the inverse matrix will simply be these positions swapped around. And then we don't really have to worry about negative 0 because that's not really a thing. So 0, 0. Now we have 1 over 1 times K, which is just K. And that's why they said K is a non-zero integer, because if it was 0, there would be no inverse of this matrix. So K, 0, 0, 1. That's how you work out the inverse of this matrix. Okay, here we have another question. Let matrix A be this matrix, let matrix B be this matrix, and let matrix C be this matrix. Find the value of x such that AX plus B is equal to matrix C. So we have to find a matrix X that satisfies this equation. And this is very neatly or disguisingly hiding the identity matrix. So what do I mean by that? We have AX plus B equals to C. If we treat this like normal algebra, the way we'd solve for x is simply minusing away b from both sides. So we'll have AX equals to C take B. And then we would simply divide both sides of the equation by A. Okay, so what we'll have is x is equal to C take B on A. Now, while this statement is true for normal arithmetic, for normal algebra, it is not true for matrix algebra. Okay, for matrix algebra, this is not true because you can't divide matrices. So how do we do this then? Okay, here's how we do it. When we have matrices, we still do the exact same steps we did before, kind of. So we still minus away B from both sides, sorry. Minus away B, so we get AX equals to C take B, but we don't divide by A. What we do is we pre-multiply by the inverse of A to both sides of the equation. We pre-multiply by the inverse of A. And why would we pre-multiply by A? Well, the reason we would pre-multiply by A is, look what I have here. I have A inverse times by the matrix A. And if I pre-multiply or post-multiply matrix A with its inverse, all that's equal to is the identity matrix. Okay, so what I have now is the identity matrix times by x is equal to A inverse times by the matrices of C take B. Another way of saying the identity matrix times by the matrix x is simply just x. Treat the identity matrix, if you're multiplying by the identity matrix, treat it like you're multiplying by 1. Okay, they mean very equivalent statements. Okay, multiplying by 1 and multiplying by the identity matrix mean the same thing. So in this case, what we can say is x is simply equal to the inverse of A times by C take B. So now let us work this out. The first step we need to do is work out what is the matrix inverse of A. So the inverse of A can be worked out like we did before. We need 1 over the determinant, in this case, is 3 times 6 minus away 1 times 2. And the actual matrix, we swap the positions of A and D, which would be 6 and 3 here. And then we add a minus sign in front of B and C. So minus 2, minus 1. 1 over 3 times 6, that's the same as 18. 18 minus 2 times 1 minus 2 is 1 over 16. Okay, and then we have the matrix 6 minus 2 minus 1 and 3. Okay, so now we have this. We have A inverse here. Let us now work out what is the matrix of C take B. Okay, we need to work out what C take B is. So we have the question up here. Okay, we have B and C right over here. And they're both 2 by 2 matrices. So to work out C take B, all we would have to do is just minus away each of the corresponding elements. Okay, so we would do 3, 4, 2, 6, minus away 4, negative 1, 2, and 2. So in this case, we would do 3 take away 4, that's the same as minus 1. 4 take away minus 1, which is 4 plus 1 is 5. 2 take 2 is 0. 6 take 2 is 4. Okay, so this is the matrix of C take B. So now all we have to do is multiply these statements together. Okay, so according to our equation, all we have to do now is x is the same as 1 over 16 times 6 minus 2 minus 1, 3 times by negative 1, 5, 0, 4. And a property of matrices is you can either evaluate the 1 on 16 now, or you can just multiply these two matrices and then evaluate the 1 on 16. And personally, I'm not really a fan of evaluating 1 over 16 into this matrix. Kind of disgusting, so I'm just going to leave it as, let me evaluate these two matrices multiplied by each other. So now let's work out what x is. X is 1 over 16 times by the matrix multiplication of these two. If you don't know how to multiply matrices, I do have another video, so have a watch of that before you watch this one. So we want to work out the entry in the first row, first column. First row, first column. 6 times minus 1 is minus 6. Minus 2 times 0 is 0. Minus 6 plus 0, that's just minus 6. Now we need the entry in the second column, but the first row. First row, second column, 6 times 5 is 30. Minus 2 times 4 is minus 8. 30 minus 8 is 22. Second row, first column, second row, first column. Minus 1 times minus 1 is 1. 3 times 0 is 0. 1 plus 0 is just 1. Now we need the second row, second column. So, second row, second column. Minus 1 times 5 is minus 5. 3 times 4 is 12. Add them together, you get minus 7. This is the matrix X, which satisfies this equation at the top here. Okay, that is how you solve for X, and that's how you can use the identity matrix. Okay, the identity matrix came in handy somewhere in our working out, and that's how you can work it out. Now we have this question here. Find Y such that Y times A plus B is equal to C. So we need to find a matrix Y that satisfies this equation. So it's very similar to the last one we did, but let's see how it's slightly different. So y times a plus b equals c. First thing I'm going to do is minus b from both sides. Same as the last question. So now I have ya equals to c take b. Now this time I need to isolate y. How am I going to isolate y if I have an a being post-multiplied? Well, I can post-multiply both sides of my equation by the inverse of a. Okay, so both sides of the equation I'm going to post-multiply by the inverse of a. The reason I'm going to post-multiply is because, again, we have a times the inverse of a, and that's just the same as the identity matrix. So y times the identity matrix is equal to c take b times by the inverse of a. And the identity matrix is just the same as multiplying by 1. So that means just y is equal to all of this. Okay, so now let us work out what is the equation here. So we already worked out what c take b was previously. And the matrix c take b, if you wanted to work it out again, is simply just minus 1, 5, 0, 4. And if you want to work out the inverse of a, let's quickly do it again. That's just 1 over 3 times 6, which is 18, minus away 2 times 1, which is 2, so 16, times by 6, negative 2, negative 1, and 3. Okay, so times by 1 over 16, times by 6, negative 2, negative 1, 3. So now our goal is to solve this equation here. If we solve this equation over here, we have the matrix of y. Okay, so the first thing I'm going to do is I don't really care about the 1 on 16, so I'm just going to leave it at the front. So y is equal to 1 over 16 times by the two matrices over here. Okay, so now let us matrix multiply this. So 1 over 16 times by, we get a 2 by 2 matrix as our final answer. So let's work it out. To get the first row, first column, we do first row, first column. Minus 1 times 6 is minus 6. 5 times minus 1 is minus 5. These two minus each other is minus 11. First row, second column, first row, second column. Minus 1 times minus 2, that is the same as 2. 5 times 3, that's the same as 15. Add them together, you get 17. Now we get second row, first column, second row, first column. 0 times 6 is 0. 4 times minus 1 is minus 4. 0 minus 4 is minus 4. Second row, second column, second row, second column. 0 times minus 2 is 0. Minus 4 times, in this case, 4 times 3 is 12. 12 plus 0 is just 12. So our answers do differ for both of these simply by the fact whether or not we post-multiply by the inverse or we pre-multiply by the inverse. Okay, so we need to just generate the identity matrix somehow doing that. And that is how you solve questions like these.